How's everyone doing? My name is Vivek Raghunathan, and I oversee AI and search at Snowflake. Prior to Snowflake, I was co-founder at an AI search company called Neva. Richard, who talked right before this, competed with me every day. He's awesome. His talk was awesome. And today I'm going to talk about something completely different. I'm going to talk about how we are going about building the most powerful SQL LLM in the world. AI is revolutionizing how our customers interact with applications that we build and the data those applications are built on. At Snowflake, we see ourselves as the data cloud. We exist to delight our customers with an Apple-like experience that is powerful, tightly integrated, and still very simple. We want to address all your enterprise data needs and delight you. Now, AI thrives on data, and as the world's premier data cloud, we think AI is a huge opportunity to exponentially increase the number of people who directly work with data. And in this ideal world, we would have users use LLMs to uncover insights, an exponentially larger number of them, without having to write SQL, without having to do messy data wrangling, without having to go analyze dashboards or analyze charts. The rest of my talk is going to focus on the core product we are building in this area. We call it the Snowflake Copilot, and it is an assistive and conversational natural language interface to data. So talking to your structured data embedded in the Snowflake first-party UX, which we call Snowsight. It's available for use for all Snowsight users as of last week. And I had a video I wanted to show you all here. The video didn't make all the various slide moves, so I will get right into the meat of it. Today, the Snowflake Copilot is an AI that helps you. It is a conversational copilot aimed at an analyst that is familiar with SQL. It takes natural language questions and converts them into SQL that an analyst in the loop can potentially refine and then execute. The interface allows for easy schema discovery and data discovery, both of which are the lifeblood of any analyst. What excites me is the future. The future is a world where we move this conversational copilot into a conversational pilot for business users. So people who don't know SQL, people who want natural language to just translate into answers, who just want to talk to the data, but understand their business really well. An interface that allows for interactive data exploration, data visualization, ultimately an AI that you depend on to get work done. And at this point, all of you are thinking, I've seen 1,000 or 1,000,000 Twitter demos about this. Surely I just saw one on Sunday. I can build this up over a weekend. Why don't you use some standard approaches? Why don't you, all the buzzwords, right? Schema rag, why don't you fine tune on a schema? There's a new leader on the Spider leaderboard every so often. So why are you wasting my time? Why are you talking about this trivial problem? And I'm here to tell you it's not that simple, right? Often in life we hit or encounter iceberg problems. These are problems that look very simple or superficially easy and turn out to be fiendishly complex. 90% of the complexity is buried below the surface. And I would posit that building a data copilot and eventually a data pilot is a problem very much in that iceberg class. The real world has messy schemas and messy data. They are large. It is very common for a database to have tens of thousands of tables, hundreds of thousands of columns. And even more so, real-world semantics are even messier. You have a table. It has 3 columns, Rev1, Rev2, Rev3. Which of these is the revenue column? Is this in US dollars or is this in local currency? Which of these was deprecated in that email that went out 4 weeks ago? Which of these is something you can rely on as the source of truth right now? It gets even messier when you go across tables. There's 3 ways to join a table, which is the right one. And these things are business critical. You do this the wrong way, you get the wrong answers. You get the wrong answers, you go and do things wrong on the business strategy side. And so it's not quite that simple in the real world. And so I'm going to tell you the story of how we built a great text-to-SQL LLM for real-world production applications at Snowflake. It's a story with many fits and starts. We screwed up quite a lot along the way, and I'm happy to walk you through every screw-up, because every screw-up came with a learning. So let me start at the beginning. In the beginning, we did what anyone working on this problem would do when they get started. There's a data set called Spider. It's published out of Yale. It's what everyone uses to evaluate performance on SQL tasks. And so we said, let's start with a single LLM across all customers. It's evaluated over and optimized for the Spider benchmark. And the way this would work is any customer-specific schema information goes into the model only in the form of the prompt. So it goes in as context. It does not go in any other way, right? And so what the fine-tuning process or pre-training process here is doing is learning to match bits of stuff presented in the schema and translate that into SQL. Now, in terms of the details, our fine-tuning is using everything we can get our hands on. So it's using natural language to SQL from the web, internal debug query logs, human eval data. We're using hundreds of base models or experimenting with hundreds of base models. And our retrieval is what you would consider state-of-the-art externally. It's embedding into a state-of-the-art embedding model and indexing in a vector database and sticking it into the context window of the LLM. This first model did pretty well on that Spider benchmark. Our best model was at 82%. For reference, GPT-4, no optimizations, so kind of being crippled a bit, 74%. I'm pretty confident if you optimize GPT-4, you'll get north of 80 as well. And on this benchmark, north of 80 is kind of the best you can get. If people tell you it's 86 versus 84, you're fitting to the peculiarities of that data set. It doesn't generalize as much. So we're good, right? Like we solved the problem. We're like at 80%, we're done. Like I can go home, I can do this talk. The talk ends right now. But not quite. We just hit our first iceberg, right? Remember I told you the real world has complex schemas. And so motivated, we said, let's switch to this internal held out data set. It was written by human annotators that worked full-time at Snowflake. It's reflective of real world use. It's complex. And so we said, let's go measure our models on this data set. Right? Our best model has 9% accuracy. So 82 went to 9. Right? GPT-4 slightly better, 74 went to 14. Right? Clearly, you cannot put in front of users a product that has 86 to 91% inaccuracies, right? It's just not doable. And remember, this was a model that we spent a bunch of time optimizing. Which brings me to my second key insight. The way to tame schema and data messiness in the real world is to build a really good semantic catalog retrieval system. And that's a mouthful, and we'll get to it. But we often take for granted how good web search is. If we can bring web quality search to enterprise metadata search and feed the output of that into an LLM, performance can potentially get radically better. In other words, to solve a simpler problem, which is what should I pack into the context of this LLM, we're going to go solve a harder problem first, which is how can we adapt a consumer-grade web search engine to the problem of conversational catalog search, right? And what is conversational catalog search? The input is a natural language query and the entire database, and the output is a scored list of database objects, the columns, the tables, the views, so on and so forth. We launched this particular product individually as a separate product. We call it Snowflake Universal Search. And when we combine it with a bunch of modeling tricks, our best model goes from 9 to 24, right? So huge improvement. So that intuition was correct. GPT-4 itself also improves, right? So why not? So that 14 becomes 28. And so, that intuition, that semantic catalog retrieval is key to solving this problem and taming data messiness, turns out to be, somewhat true. Here's a quick architecture diagram of how conventional catalogs, of how conversational catalog search works. Schemas, metadata, sample values, these are flowing in from the left from Snowflake. From the right, user queries are coming in. The user queries are going through a query understanding layer. There's multi-turn disambiguation, there's query rewriting, every known trick from the IR and NLP literature. And in the middle is the box where we're taking a consumer-grade search engine, Neva, and then adapting it to the problem of conversational catalog retrieval. And so it has sparse and dense retrieval, sparse and dense ranking, so keyword retrieval, bi-encoder LLM for retrieval, IR ranker that's far better than BM25, and a cross-encoder LLM for ranking. And of course, all the usual secret sauce in search, right? You train these models on the web and schemas, you stick in popularity, authority, freshness, you do lots of elbow grease, and then you have a system that you like. After building the system, the product is going towards private preview. We're ready to get our first customer. We hit our second iceberg. I remember us debugging why single table performance, which is generally like the easiest of the text to SQL problems, was so crappy. And then we realized that the eval set we were using had lots of subtle but messy errors. In other words, we had gone from a data set that was too simple but correct, spider, to a data set that was more reflective of real world use, but had subtle errors. Right? So what is the crux of the issue here? The crux of the issue here is, for those of you who write SQL, it isn't easy. You have to, it's not just learning the syntax, it's learning the underlying semantics of the data. It's learning to think like an analyst. Our raters were not highly paid analysts. And even an analyst will take an hour to understand a database before they have a very structured process of learning how data is structured before they will go and write queries. And there are multiple other crazy issues. There's join paths between tables can mess you up. There's these, you can Google these things up or use u.com, chasm traps, fan traps. And in other words, we've hit the iceberg, which is we must rate the rater, right? And so, with the problem thus identified, the solution is pretty simple, right? We reannotated everything by hand. We did multiple rounds of this. We validated it. We cross-checked it. The cross-check is actually harder than you think it is because it truly needs you to try solve the problem. There can be lots of apparently correctly sounding things. This happens in the summarization literature as well. You take some complex piece of text and summarize it. An LM can generate something that looks reasonable and it's actually wrong. At times we had my co-founder Sridhar, who's now the CEO of Snowflake, be a rater. So we used very expensive raters. Then we sliced all the data. We made sure that we had a measure of complexity and performance was monotonic in complexity. And after we did all this, our best model, we're rebaselining the models we're trained, now at 27%, GPT-4 with our optimizations, now at 40%. But most importantly, we can trust that our foundation's on solid footing. So with the house now on a solid foundation, we turn to doing what we all really want to do, which is let's go do a bunch of modeling work, let's go do a bunch of signals work. So better base LLMs. Turns out code LLMs do really well on the SQL task. So if any of you is trying to build one of these, first use us, but if you want to build it yourself, use a base model that is derived from code. Better signals, some from LLMs, for example, comments. Some from classic techniques, for example, Snowflake documentation. And the one I like most, query history, is a treasure trove of what people actually do. Chain of thought ideas. So first you pick the tables, then you pick the joins, then you pick the columns, then you aggregate. And then checking correctness at decode time. So when you all see LLMs produce JSON, there's a dependency parser that is you can think of conceptually as checking that the output matches the schema. Except here, the schema is infinitely more complex. With this new clean eval, now we are 27 has become 39, 40 plus has become 46, and you can see the arc of things are improving. And then we hit our third iceberg, right? So what is this iceberg? Our model, in trying to build a great zero-shot text-to-SQL model, we have made it great at SQL, text-to-SQL, and we have crippled it at other things, right? But the product we're trying to build is a conversational copilot. It has to be able to have conversation. It has to be able to let the analyst refine things as they go along. And so in optimizing for one part of our system, we'll kind of, unoptimize the whole thing. Two big issues: our model stopped becoming great at instruction following because the only things it saw were text to SQL. Second one, it became poor at conversation because it never saw multi-turn cases. It only saw zero-shot cases. So we jeopardized the product, which is not good. Again, with that problem clearly articulated, the solution turns out to be fairly simple. First, we retrained our LLM to do instruction following. So we gave it a mix of text to SQL tasks and more general purpose instruction following tasks, so it didn't forget to do instruction following. And then we layered it in a multi-LLM setup where there's an orchestrator LLM, if you will. We used Mistral Large because we had access to it, and the Mistral people are amazing. And that model is essentially like its responsibility is have a conversation with the customer, and we give that model a tool. We tell it, you're allowed to use this other equally big model, a text to SQL model, whenever you think you need to write SQL. And it turns out doing that and abstaining smartly solves a lot of problems. So how do our numbers look? On that same cleaned up eval set, if we just use Mistral Large, this is just like a baseline, that's 39%. If you use our best model, you saw it used to be 38, now it's like 41. That's because we added instruction following in there. If you take GPT-4 and all our optimizations that we baked in, that's at 46. And this new setup is at 46.5. When I checkpointed this, probably higher at this point. So lots of elbow grease. We now have a model that is best in class, but we're going to hit our fourth iceberg, right? It's great to look at these relative numbers and say, we're making lots of progress, but if I pop up and say, what are we eventually trying to do? We're eventually trying to build a conversational pilot for business users, and they don't know SQL, right? And that is the opportunity, and they need 99% accuracy. So if you want an AI you depend on, you need accuracy so high that you can run the SQL, give the answer, and no one feels like they have to second guess. And so we need that near perfect accuracy. And we're working on it. It is still a work in progress. We are going about it using a number of clever ideas. The key insight is we need to understand the data and encode it programmatically and feed it to the LLM. So which columns are dimension columns? Which columns are metric columns? When they are metric columns, are they summable, or do you have to average them? If they're a dimension column, what are the primary keys? What are the foreign keys? Like, what are the join paths? What are the join relationships? So all the stuff that doesn't live in AI ML and tends to live in the data world has to be brought to the LLM. You can do this two ways. There's a bunch of business tools, business intelligence tools that customers will go spend laborious amounts of time keeping this stuff curated. They're called semantic layers. You can ingest that. We can also algorithmically generate it. People issue queries, so query history tells you what stuff is still live and how people typically join. And so you can use some combination of algorithmic and human curated to get there. We're doing a bunch of clever things. I will hold off on reporting exact numbers. My team will kill me. But suffice to say, I don't feel stressed out by this goal. Progress is very, very promising. So what did we learn through this process? I want to wrap the talk by popping up a level and just synthesizing, because I think these learnings are true for almost any real-world production LLM you have to deal with. The first, lesson one, it sounds obvious. All these lessons sound obvious. You just go through bruising battles to learn them. The product is the entire end-to-end system, right? It is not like your little one subcomponent. We made great text to SQL and we screwed up the conversational capabilities of the product. The second one is, let me go back. Semantic catalog retrieval is critical to taming the complexity of real-world data schemas. Most people will just take stuff, they will index it, they'll stick it in a vector database, they'll get something coming out of the vector database, they'll shove it into an LLM, and they'll hope everything works, right? I would say that part, powered by a real AI search engine, actually evaluate how you're doing, make sure that thing rocks, because just saying that an LLM has a million context window or whatever and hoping it'll work is generally doesn't do as well. Lesson 3, annotation quality for SQL is paramount. Please rate your raters. If you need experts, use them, because the alternative is you'll do a bunch of busy work and go nowhere. Lesson 4, which was new to me, I had gone in thinking text to SQL is easy, conversational SQL is easy, but it seems like it's a little bit of a LLM Grail problem. It is much more complex than, the human eval metric for code, or it has all the aspects of what make LLMs interesting to me. Complex instruction following, there's chain of thought, there's tool use, and I expect we'll see agentic workflows make a meaningful dent at this problem. And finally, I think getting to 99% is going to need a breakthrough. So I'd watch this space, I'd watch what we're doing. I feel fairly confident. And at this point, I'll stop and hand it back